Unit 3, Part 6. Okay, we've calculated that this formula here is false. It is a conditional and it's false. Compare this one. Okay, again, A is true. So notice that we have the same sequence of symbols. If you abstract from the parentheses or brackets, right? You've got A, or, Y, hook, Z. Here again, we've got A, wedge, Y, hook, Z. But these are not equivalent formulas. The parentheses indicate a different order of construction, right? Right. What is this? What is this? It is a conditional. Why? Its major operator, that is the last sentential operator used in constructing this formula, is a conditional. It is a conditional with the antecedent as where the antecedent is a disjunction. What is this? This is something else. What is this? This is a disjunction. This is a disjunction because the major operator is a disjunction. The last sentential operator used in the order of construction was a disjunction, right? Because here, with the parentheses here, right, this means first I'm given the atoms A, comma, Y, comma, X, right? And then, second, I made a conditional of Y hook X, and then finally, I took that Y hook X and I disjoined it with A, right? So the last in the order of construction, so the order of construction of this one is, right, A, comma, Y, comma, X. Then I made Y hook X, and then after that, I made a disjunction with that and A. Sorry, that's extremely ugly. But right? Order of construction there. Order of construction of this will be different, right? First, in the next step, you'll have the wedge, right? And then in the final step will be the hook. The major operator is the hook. But this is different. So when I'm computing this, look how I compute differently, okay? Again, A is true, Y is false, and X is false, okay? So now, should I go and determine this? Well, let's think it through. The answer is going to be no, but let's think it through. It's a disjunction, right? Well, there's a couple of lessons to teach here. It's a disjunction, which means the disjunct is true so long as at least one of the disjuncts is true. Right? The disjuncts being the things destroyed. Okay, well, is this, right, I've got F here and F here, is the right-hand disjunct true or false? I don't know yet. Okay, so usually I have to first compute this because I need to know whether this is true or false to determine whether this is true or false. In this case, I don't actually. I can already determine that this is true because one disjunct being true, as this one is, suffices for the truth of the disjunction, right? So notice the application of the truth tables there. And a lot of what you'll be doing is sort of applying your truth table knowledge to shortcuts in this way. I'll give you a few more examples in a second, but see here, the answer to the overall question, the answer to the final question, is this formula as a whole true or false, can be given, yes it is true, without calculating this, right? Because I know that this is true, A is assigned true, that suffices, that is sufficient for the truth value of the overall thing, right? So this disjunction is true whether this is true or false. If this turns out to be true, it's true. If this turns out to be false, that's false. What is that? That's an application of the knowledge of the truth table for the wedge. I say that knowing that T hook T is true and T hook F is true. I'm in one of those two cases. Before I calculate this thing, right, the truth value of P or Q, remember, right? T, 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 F, F, T, F, F. It's T, 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 F. Right, what do I know? I know that my P is true. Here, A is the substitution instance for the variable P. The substitution instance for the variable Q is Y hook X. What? I can substitute something Y hook X for Q? Yes, you can, because Q is a sentential variable taking as substitution instances formulas of whatever complexity. Any legal formula can be Q, right? Any legal formula can be substituted for these, okay? We'll be learning this lesson over and over again. But that's enough to say that this is true. But usually what I do is I go F hook F. Okay, is that true or false? Well, F hook F is actually true, knowing my thing. Like I'm just looking, applying my knowledge of what the fourth row of the truth table for the hook is. When P is false and Q is false, P hook Q is true, right? So it's true. And T wedge T is T. Okay, so we say a bit more, looking forward a little bit, I'll give you a bit of a taste of what the proofs are going to look like. So I've told you a bit about the form. I've mentioned the form modus ponens, the first argument form, the first valid argument form given in the inside cover of your book. It's P hook Q, comma P, therefore Q. Right? That's a valid argument form, a set of sentence forms. Okay, so that P hook Q. Well, let's go with the second one. All right, modus tollens. Right, it's P hook Q. It's this P hook Q, not Q, therefore not P. Right, you've got a conditional. You've got a negation of the consequent. You're entitled to infer the negation of the antecedent. That's what that says. Okay, you're going to be, when you do proofs, 7 to 9, you'll have to learn to recognize things like this. A by conditional B, right, hook, not G hook S. Okay. Okay, look at that. Okay. You might have, in proofs, you'll be giving a set of premises on a vertical line, but you'll have to be able to see, right, G hook S. You'll have to be able to see that when you're given premises like this, or when you've otherwise derived two formulas of this form, you are going to need to be able to see this form, especially this form, in these two premises, right? That's why you need to learn to speak the way I'm encouraging you to speak, right? Expressing the logical form of the formulas, right? You need to be able to say, what am I given with these two premises, or these two formulas, right? I am given a conditional, and I am also given the negation of the consequent of that conditional. Right? This is a conditional, and look at this, not G hook S, right? And that's the same as that. And there's another negation sign there, right? These already look ugly and complex, but this is where we're going. So this is a conditional, where the antecedent is itself a biconditional, and the consequent is the negation of a conditional, and this is a conditional double negated. But you need to see this as an instance of that, right? It's a substitution instance of this. This is a rule, right? This is modus tollens, a valid rule of inference, and what it says is that this is how you have to say it, this is how you have to think it, such that you can see this. This says, whenever you're given a conditional and the negation of the consequent of that conditional, you're entitled to infer the negation of the antecedent. That's what that says. If you can say it like that, and if you know it like that, then you can see it in this. Right? Here I have a conditional. Oh look, I'm also given the negation of the consequent. I'm entitled to infer what? Right? We'll have next rule 3, not brackets, right, A by conditional B, by the rule of modus tollens, based on steps 1 and 2. Right? Don't worry too much about that, but that's where we're going. The point is, a lot of what logic will be learning to recognize the simple forms with which we have to deal in more complex particular instances. But it'll also be true even in just computing truth tables. So the big questions in the exam are going to be, use the full truth table method. Something like, use the full truth table method. This is what Unit 5 will teach. Use the full truth table method to show that to test this argument form for validity. right? And you will have things like, you know, complicated formulas like this, except with P's and Q's. But it's just a iterated application of the truth table at each step, right? As you work through the construction of the formula to figure out the truth values of the overall formula, right? So as we'll see how that works out as we continue.